Okay, so Junior Robert here. This is a sample question from the January 2012 CSEC Physics Paper 2. Right, this is a thermal physics question. So let's go right into it. So the question says, Figure 5 shows two blocks of copper that are placed in contact with each other. Block A initially has a temperature of 40 degrees Celsius and block B has a temperature of 70 degrees Celsius. So question 1 says, what is the direction of net heat transfer between the blocks? Right, so here we have our two blocks. Right, this is block A at 40 degrees Celsius and block B at 70 degrees Celsius. Now they want us to actually show the direction in which the net heat will travel, the direction of net heat transfer. So what to know about the direction of net heat transfer is that the direction of net heat transfer is always from the hotter object to the colder object. So therefore in this case we're going to have a net heat transfer from the hotter object, in this case block B, which is at 70 degrees Celsius, to block A, which is at 40 degrees Celsius. So we're going to have heat traveling this way, right, from the hotter object to the colder object. So we could make a statement that the direction, right, so we could say that the direction of net heat transfer will be from block A, well, block B, I should say, block B to block A. Right, now the next question, it says that the final equilibrium temperature of the blocks is 52 degrees Celsius, and they want us to convert this temperature to Kelvin. So what they're basically saying with this question, after some time, right, after these two blocks are in contact with each other, they reach a temperature in which both blocks share the same temperature, which is the equilibrium temperature. So at the equilibrium temperature, there will be no net transfer of heat or net heat transfer. So what I want us to do is to simply convert this temperature in degrees Celsius to Kelvin. Now to do this, what we simply need to do is to add 273 to our temperature in Celsius. So we're going to say 52 degrees Celsius plus 273. So if we add 52 degrees Celsius and 273, we're going to get 325 Kelvin, right? And that's our temperature converted from Celsius to Kelvin. So 52 degrees Celsius is the same as 325 Kelvin. So let's now move on. So it says figure 6 shows the sketch of a natural convection solar water heating system, right? And we have our diagram right here. We have our solar collector, right, with our copper tubing, our insulation, and our black surface, and we have a glass that encloses everything, and then we have pipes for hot water and cold water, and we have our reservoir, right, or our hot water tank. So let's see what this question wants us to do. Right, so the question says the energy absorbed by the solar collector is 300 kilojoules, and 40% of this energy is transferred to the 2 kilograms of water in the copper tubing. If the initial temperature of the water is 27 degrees Celsius, calculate the final temperature of the water. So to do this, right, we're going to consider the equation, right, which says that the thermal energy, right, we're going to call it EH, thermal energy or heat energy, right, supplied or removed is equal to the mass of the substance multiplied by the specific heat capacity of the substance multiplied by the change in temperature, right? Now this equation can also be written as Q is equal to mc delta theta, right? It's the same thing, right, where the thermal energy is equal to the mass multiplied by the specific heat capacity multiplied by the change in temperature. Now for this question, they told us that the energy that was absorbed, right, from the sun by the solar collector was 300 kilojoules, and 40% of that energy went into the water, right? So what we need to do is we need to find 40% of this energy, right? Now we know that 300 kilojoules, right, is the same thing as 300,000 joules, because what we do is simply convert from kilojoules to joules by multiplying by 1,000. Right, so multiply 300 by 1,000 and get 300,000 joules. Now what we need to do now is to find 40% of this. So we're going to say 300,000 joules divided by 100 multiply by 40. Right, and when we do that, let's take out our calculator, and we're going to say 300,000 divided by 100, right, multiply by 40, right, and we get 120,000 joules, right? So therefore 120,000 joules was actually transferred to the water in the copper tubing. So now we can use this as our energy. So we're going to write that our energy in this case will be 120,000 joules. That is equal to the mass. In this case our mass is 2 kilograms. So we're going to say 2 kilograms multiply by, since we're talking about water and we know that the specific heat capacity of water is actually 4,200 joule per kilogram per Kelvin, right? That's the specific heat capacity of water. So we're going to now say that 2 kilograms multiplied by the specific heat capacity of water, which is 4,200 joule per kilogram per Kelvin, right? And that is multiplied by our change in temperature. I'm going to write that as delta T, right? Now, when we consider delta T, right, delta T is our change in temperature, and our change in temperature, delta T is equal to the final temperature, right, minus our initial temperature, right? So then now we can simply write that 120,000 joules is equal to, we can simplify here, so we're going to simplify this portion, right? So we're going to simplify this by multiplying them through. So we'll multiply 2 kilogram by 4,200 joule per kilogram per Kelvin. We're going to say, take out our calculator, right? And we're going to say 2 times 4,200, right, is 8,400. 1,400. Now, in terms of our units, we have kilograms here and we have per kilograms here. So these two will cancel, leaving our unit being joule per Kelvin, right? And we have delta theta, which is our change in temperature, which is again the final temperature minus the initial temperature. Now in this case, we want to find the final temperature. So our final temperature is the unknown, but we are given the initial temperature, which is 27 degrees Celsius. Now, since we're working with the unit Kelvin, we can convert this to Kelvin. So we're going to convert to Kelvin by simply adding 273. So we say 27 plus 273, right? That will give us an answer of 300 Kelvin, right? So TF, so this is TI, I should say, is equal to that, which is equal to 300 Kelvin, right? So we're going to have our final temperature, again, that's TF, right, minus our initial temperature, which is what we just converted right here to 300 Kelvin. So we're going to have 300 Kelvin, right? Then we can start to simplify further. So what we're going to do to simplify further, we're going to divide both sides by 8,400. So we divide here by 8,400 joule per Kelvin and divide here by 8,400 joule per Kelvin, right? Now when we take this side and simplify this side, we're going to get, taking our calculator, right, we can say 120,000 divided by 8,400, right, gives us an answer of 14.29, right? So we're going to say 14.29, and in this case for our unit, right, joule will cancel joule, and we have per kilogram right here. It's in the denominator, so it's going to come up to the top as Kelvin, right? We have per kilogram is going to come to the top as Kelvin. So Kelvin, and that is equal to our change in temperature again, which is TF minus TI, which is 300 Kelvin, right? Now what we will simply do from here is to add 300 Kelvin to both sides. Right, so we're going to add 300 Kelvin to both sides so that we can get rid of this negative 300 Kelvin. Now when we do that, we're going to see that TF is equal to 14.29 plus 300 is 314.29 Kelvin, right? Or we can convert back to Celsius, right, by simply subtracting 273. So if we say 314.29 minus 273, right, we get 41.29 degrees Celsius, right, and that's our final temperature. All right, now let's continue. So here it says we are to outline which feature of the solar water heater system shown in figure 6 demonstrates each of the following thermal principles. So for good heat absorption, we can look back at our diagram, right, and we see that we have a black surface here, right? Now we know that dark, dull surfaces are good absorbers of thermal energy. So therefore this black surface is responsible for being a good thermal absorber. So we can say good absorption of heat. We're going to say black surface. Right? Now next thing now, right, it says heat transfer by convection. Right? Now here we have our system like this. Right, now this reservoir is what will actually contain the water. Right, now what we will have is we will have hot water coming in. Well, hot water is less dense, so it's going to rise to the top, and the colder, more dense water will fall to the bottom and then actually flow through these pipes into the solar collector here, and we're going to have that water being circulating due to convection. Right, so therefore we can say that the reservoir and the pipes, right, so we can say reservoir, reservoir, right, and pipes. Right, now for the greenhouse effect, again we can look back at our diagram, right, and we see that we have a glass here. Right, now what this glass is responsible for is to trap in any unabsorbed radiation or thermal radiation from the sun that actually passes through. Right, so we're going to have high energy thermal radiation passing through. Some will be absorbed by the copper pipes or copper tubing, while some will want to be reflected out. Now because this glass is right here, it will actually prevent any reflection of that thermal radiation, and it's going to keep inside here warm. So the glass is responsible for the greenhouse effect. So we can say that the glass will be responsible for that. Now good heat transfer by conduction. Right, again looking back at our diagram, we have our copper tubing right here. We know that copper is a good conductor of thermal energy, and it's going to be responsible for conducting the thermal energy from this dark surface into the water that is actually housed inside this copper tubing. So we're going to say our copper tubing, right, and then finally the reduction of heat transfer by conduction. Again, quick look at our diagram, right, and we see that we have some insulation here. Right, we know that the purpose of this insulator is to actually prevent any wasting of thermal energy to the environment. So by conduction, and the material that is responsible for that is the insulation here. Right, so for this we're going to say insulation. Right, so again, this was Junior Roberts with realjuniorroberts.com. If there was anything in this video that you wish to get further clarification on, then post it below in comments, and I'll do my best to clear up any misconceptions for you. Like this video if it was helpful, and click subscribe on the bell notification so you'll be updated whenever I post new videos like this. Thank you for watching.